we're going to look at this problem now, which is how many hydrogen atoms there are in 72.5 grams of C3H8O. So in this particular case, when we come across a problem like this, we are not interested in the entire thing. We are really just interested in the hydrogen part of it. So we have to have a way to go from the entire formula here to just the hydrogen part. In addition, we also have the word atoms there, which means somewhere along the way, we do need to use Avogadro's number to do that. So in a situation like this, where you may not be interested in the entire thing, but just interested in one aspect of the formula, we have the actual formula itself that we could use as a conversion factor. And the way that we could use the formula as a conversion factor is when we look at these little subscripts that are present, these do represent basically the moles of each of these guys that we have. So we could actually use that to our advantage here, and we could say that in 1 mole of C3H8O, there is 3 moles of just carbon. And again, that comes from our subscript that's on the bottom. And 1 mole of C3H8O, we could see that there would be 8 moles of hydrogen. And in 1 mole of this entire thing, C3H8O, there would be, obviously, if nothing's written there, that would be 1 mole of oxygen. So we could actually use the formula itself as a conversion factor, which is a mole to mole conversion factor. That is what's going to basically help us understand how we should do this problem. So since we are only given grams here, before we could even use our mole to mole relationship, we do need to take those grams to moles. And that is what we did before, which is our molar mass to do that. That then would allow us to use this middle conversion to go from moles of the entire thing to moles of just the hydrogen. And at that point, once we have it at just hydrogen, we're good to go with our Avogadro's number to complete the actual problem. So one of the first things we've got to do then is to figure out the molar mass here of this compound. So we have 3 carbons, each at 12.01 grams per mole. We have 8 hydrogens at 1.008 grams per mole. And we have 1 oxygen at 16 grams per mole. So this is going to give us our molar mass of this entire compound here. And again, that's going to be pretty much what we saw before, I think. It looks familiar. That's our 16. It's going to be our 6009 grams per mole here. So the first thing we want to do is take what they gave us, which was 72.5 grams of the entire thing. We want to use the molar mass opposites cancel, which are grams, 6009 grams per mole of the entire thing here. The grams are going to cancel at this point, and that's going to give me, if I get an answer, which again, you don't necessarily have to, but if you want to get an answer, 1.206. And again, I'm not going to round too much at this point, moles of the entire compound here. So very similar to what we did previously, but the important part of this conversion is it gets it into moles. And now that opens up this conversion here, which is our moles to moles. And that's what's going to allow us once again here to go from the whole thing to just the hydrogen part. And if we do that, we're going to again do opposites. So 1 mole of the entire thing gives us 8 moles of hydrogen. So using the formula itself is going to allow us to do this conversion. And at that point, once again, if you did want to get a number, they're going to times it by 8. That's going to give us 9.65219. Again, not rounding too much at this point. Moles of hydrogen. And now that we have it in moles of hydrogen, we're pretty much at this point, we're going to use Avogadro's number there to go the rest of the way. And we'll continue on with our number here. And at this point here, we do want moles on the bottom, our Avogadro's number here up on top. And again, this is going to be atoms now since we're just talking about hydrogen. The moles will cancel. And that would get us at this point here, multiplying by Avogadro's number. We got here 5.81 times 10 to the 24 atoms of hydrogen. So again, here I did get an answer at every spot, which you don't need to do. You can just go from here to here to here all in one calculation without the answers in between. Once again, like normal, if you need to get an answer, do not round too much till the very end. Any questions on that? We obviously could do a very similar calculation with if we were just interested in just carbon or interested in just oxygen. We also could figure out, for example, from this point, how many grams of hydrogen that would be, right? By using the molar mass. And we could also do that, obviously, for carbon and oxygen as well. So there's a few endings that you could kind of go with, also using the molar mass and Avogadro's number. Clearly, if we were going to do the grams at the end here, it would need to be just hydrogen, right? Because that is, again, hydrogen at this point that we're using. Any questions on that there? All right, let's try this one here. So why don't you do, what is the mass in grams of one molecule of caffeine? And then why don't you also do how many grams of nitrogen are in one molecule of caffeine? All right, so work out both of those, see what you come up with. Again, carbon 12.01, hydrogen 1.008. Got lost my 12 there. And nitrogen 1401, and oxygen still 16. Okay, so let's take a look here, see what we got going on. So we got what is the mass in grams of one molecule? So molecules in play, which means Avogadro's number needs to be used. That Avogadro's number will take us to moles, and then we could go from moles to grams using the molar mass at that point. So we need to calculate the molar mass here. So let us do that. That is 8 carbons, it looks like. So we got 8 times our 12.01 for our carbon, plus our 10 times our 1.008 for our hydrogen, plus 4 times our 1401 for our nitrogen there. And lastly, 2 times 16 for our oxygens. So that's going to give us a lot here. 12.01 plus 10 times 1.008 plus 4 times 14.01 and 32. It's like 194.2 grams per mole. So that's going to be our molar mass that we're going to use here. So we'll start with our calculation. We're going to go one molecule here of our thing. C8, H10, and 4O2. Here we will use Avogadro's number to get us into moles. So we're going to divide by Avogadro's number here, which would be molecules on the bottom, moles up on top. Molecules will cancel. Now we can use our molar mass here, which is 194.2 grams up on top per mole. That way the moles will cancel. And that's going to get us here basically 194.2 divided by Avogadro's number. Give us something like 3.225 times 10 to the minus 22 grams here of caffeine. I don't feel like writing the formula there, so I'll just write caffeine. There we go. Any questions on that calculation? Here, I went to four significant figures based off the molar mass, since one would be kind of like an exact number. If you had one something, you would just count it. So I just went with four significant figures based off of the molar mass in this particular case. Question on that there. All right, second one I made up here is how many grams of nitrogen are there in one molecule of caffeine? So here we need to go get it into moles, and we also need to use the formula here as a conversion factor. So we could see that in 1 mole of caffeine from this formula here, there is 4 moles of nitrogen. Again, before we can really get it into using that, we do have to get it into moles. So that really is the first part of the calculation we did above. We could use Avogadro's number there to basically get it into moles. And at that point, we could use that relationship to get it to just nitrogen. So if we do that, we would actually start this calculation the exact same way. 1 molecule of our caffeine. And again, using Avogadro's number on the bottom so that we end up with moles up on top. Again, of this whole thing here. Molecules will cancel. Now that we do have it in moles, we can use our conversion factor that we got from the formula. And again, you can get an answer, or you can just continue on. So I'm just going to continue on. We want to put the moles of the whole thing on the bottom. And that is 1 mole of the whole thing, and that will give us 4 moles of nitrogen. If I stop the calculation right at this point, I'm in moles of nitrogen, which is close to what I want. I do want grams, so the last thing that I need is the molar mass of nitrogen from the periodic table, and that is what we would use on the back end here. We do want to end up with grams, so we're going to put grams up on top and moles of nitrogen on the bottom. They will cancel, and that's going to leave me with grams. So in this case, we're going to take 4 times 1401. We're going to divide it by Avogadro's number, basically, here. And that's going to give me 9.306 times 10 to the minus 23 grams of nitrogen is basically here. I'll write it on this side here, 9.306 times 10 to the minus 23 grams of nitrogen. Any question on these calculations? So clearly going from grams to moles, moles grams, something we do a lot in chemistry. You need to be very proficient in doing that. And in these certain cases, sometimes, like I said before, you're asked not about the entire thing, but maybe just about an element in a compound. You can use the actual formula itself as a conversion factor. Any questions on any of that there? All right, then let's talk about percent composition by mass. Percent composition by mass is basically the mass of the element you're interested in divided by the molar mass of the compound. You times it by 100%. And obviously, if we have 100% of the compound, all of our percent composition by mass should equal 100% when it's all said and done. So we take a look at ethanol, which we calculated the molar mass of this guy earlier in a problem, and it was 46.07 grams per mole. We can figure out the percent composition of each of these elements. So the percent composition, for example, of carbon in this case. There are 2 carbons. which means we need the mass of just the 2 carbons to go up on top. So that'd be 2 times our 12.01 divided by the molar mass of the entire compound here. And we're going to times it by 100% in this case. And that's going to get me about 52.14% carbon this compound's made up of. We could do similar calculations for the other elements that are present. So if I wanted the percentage of hydrogen, I would look at the formula and see that there are 6 hydrogens present. So on top needs to go the mass of just the hydrogen. So 6 times 1.008 grams per mole. Again, divided by the entire molar mass of the compound times 100%. And times it by 100 will give us that it is 13.28% by mass hydrogen. And obviously, lastly, at this point, we could do our percentage of oxygen. In the case here, we actually just have 1 oxygen in the formula. So that is just the molar mass of 1 oxygen up on top, which is 16 divided by 4607 grams per mole. Up times about 100%. And that will get us here 16 divided by 4607 times 100%. 3473% oxygen. Now, obviously, if we add up all those percentages, it should add up to about 100, which I believe it does, which is good. That also means that once I've had the percentages of hydrogen and carbon, I could have got the percentage of hydrogen by just taking 100 minus those percentages, right? So that would give me my sort of last percentage as well. So instead of doing the calculation for that last element, if you have the percentages of the others, you basically could just subtract 100 from it, or 100 minus those percentages. Question on percent composition by mass of each element in a compound. Basically just going to take the mass of the element divided by the molar mass times it by 100. Any questions on that there? So percent composition by mass is very commonly used with empirical formulas and molecular formulas. They give you sort of the percentage of each of the elements in the compounds, and you could use that information to calculate something like the empirical formula or the molecular formula. So let's talk about those things, which is basically those 2 formulas. So the empirical formula, like we did in that lab, is the simplest whole number ratio of what is present. While the molecular formula will tell you exactly how many of each atoms are present. So for example, if we had H2O2, hydrogen peroxide, as our molecular formula, that basically means that there are 2 hydrogens for every 2 oxygens. That basically can be reduced down by 2, and that is the same ratio as 1 hydrogen for every 1 oxygen. The empirical formula for that guy would be HO in that particular case. If I had C4H8O2 as my molecular formula, that is a ratio basically of 4 carbons to 8 hydrogens to 2 oxygens. That also could be reduced down by 2. And that could give us basically, if we reduce everybody down by 2, that would give us 2 carbons to 4 hydrogens to 1 oxygen. And that would be our empirical formula for that guy. It would be C2H4O. So if you could reduce down a molecular formula and divide everybody by a common number and still end up with whole numbers, then that would be your empirical formula that you could get for it. Now, there are certain cases where, for example, water is 2 hydrogens for every 1 oxygen. That is pretty much as far down as you can go. You cannot reduce those guys down anymore and still get whole numbers. So something like water, H2O, is both the empirical formula and the molecular formula. They're the same. So there are certain things that you just can't go any further down to reduce it by. Now, when we talk about empirical formulas are pretty much the ones that are very easy to determine through experiments. Again, like experiment 7, you basically just weigh the mass at the beginning, weigh the mass at the end, and do some calculations, and you can very easily sort of figure out empirical formulas. All ionic compounds are empirical formulas. They're formulas. So if you think about an ionic compound, when you write the formula for it, you want to put it together so that you end up with the simplest way to get to 0, where they're all whole numbers. So all pretty much ionic compound formulas are always going to be empirical formulas and be reduced down to the simplest, basically whole number ratio that's present. Any questions on that there? Now, we could actually calculate empirical formulas like we talked a little bit about there in lab. So to calculate the empirical formula, a couple of things that you want to follow. So first off, if you're given the percent composition by mass, usually a good way to convert percentages into numbers is to assume that you have 100 of something or 100 grams. What that will essentially do is turn all your percentages into grams. And you could keep all the numbers the same. You could assume as many grams as you want, but the numbers would change. So if you keep it at 100 grams, then whatever percentage is how many grams that you have. Once you have that, then you want to, as we talked about, take those grams for each element and basically convert them into moles. So obviously that is our molar mass calculation that we've been doing to do that. Third step is we want to divide by the smallest number of moles. And again, as a couple examples that we talked about, if we did number 2 and you had again something like 2A and 6B in terms of moles of these guys, so 2 moles of A and 6 moles of B, you can divide each of these guys by the 2 moles, which is the smallest. And that would give us obviously here 1 for A and 3 for B. And that would mean our empirical formula would be AB3. We got all nice, pretty kind of whole numbers in that case. As we also talked about, you don't always get pretty whole numbers. So again, if we had 2 moles of A after doing step number 2, and again, 5 moles of B, and we divided by our 2 moles each of these guys, that will give us 1 there, and we got 2.5, I believe, moles for this guy. And in that particular case, that would give us an empirical formula AB 2.5. Once again, it does need to be whole numbers there on the bottom. So as we talked about, you do need to figure out a factor in this case to multiply the 2.5 by to get to a whole number. So obviously 2.5 times 1 is 2.5. 2.5 times 2 is 5. So that is the factor that you want to multiply this guy by and this guy, everybody in the empirical formula by, to get the proper empirical formula, which in that case would be A2B5 would be our proper empirical formula. So in textbook type problems outside of the lab, in textbook type problems, it usually needs to be pretty darn close to that whole number for you to be able to round. So just below the whole number, like 0.99 something or 0.98-ish, 0.97, or just above the number, like 0.02 or 0.03. I would say if you're starting to get into, you know, the first decimal place of the numbers there, that's maybe a situation where you might be too far to round. Typically, if too far to round has common endings of like 0.33 is a common ending. 0.50 also a common ending when you divide. So those are again considered too far to round. You would need to figure out a factor to multiply it by to get to a whole number. Any questions on that there? All right, so let's take a look here at one. Why don't you give it a go? We have, we want to know the empirical formula here. If this compound is made up of potassium, that's 24.75%, Mn, that is 34.77%, and oxygen, that is 40.51% by mass. So we'll give you some numbers here. We want potassium, 3910. Mn is 5494. Mn. And our oxygen still 16. There we go. All right, so calculate the empirical formula, see what you come up with. Follow. Okay, let's take a look here and see what we need to do. So obviously, first thing you probably want to look at, move our potassium over, is just take a quick look at the percentages. And again, you want to make sure that it does equal 100%. And if it doesn't equal 100%, then you are definitely missing something along the way. In this case, we do have about 100%, so we could assume 100 grams. And that basically will just turn these percentages into grams. So we'll have 24.75 grams of potassium. We'll have 34.77 grams of Mn. And we'll have 40.51 grams of oxygen. Next thing we want to do is take those grams and convert them into moles. So that is the molar mass from the periodic table to do that. So we're going to go with 3910 grams per mole of potassium. We'll go with 54.94 grams per mole of Mn. And we will go with 16 grams per mole of oxygen. And we'll get our moles of each of our elements, which is what we need to kind of continue on here. 0.63299 moles of potassium. Again, I'm not going to round too strictly here. And take it to a few extra digits. Never really hurts too much to do that. 0.63287 moles of Mn. And lastly, 40.51 divided by 16 gives me 2.5319 moles of oxygen. So in this case here, we're going to divide by the smallest. They look fairly close, so we'll go with Mn as our smallest here. So we're going to divide everybody by the moles of Mn, so 0.63287. 0.63287 and 0.63287. When I do that, that is going to give me a 1 there for my potassium. It's basically going to give me a 1 for my Mn. And lastly, for my oxygen there, it is going to give me a 4, basically. And we did hit pretty much all whole numbers when we did that, which means that should be our empirical formula, KMnO4, a little potassium permanganate here. Any questions on those steps there? Okay. So clearly, much like the lab that we did, this is a very common sort of empirical formula type calculation. Let us talk about another type of calculation, empirical formula calculation, which is one that is done through combustion analysis, which is a little bit different than how we did the experiment. A combustion analysis involves a combustion reaction, and the most common combustion reaction that we do this with is we take some type of organic compound that contains usually the elements carbon, hydrogen, and oxygen sometimes. We add oxygen to it and go through a combustion reaction. And typically speaking, when you do an organic combustion reaction, you will always produce carbon dioxide and water. Now, when we do this type of reaction and analysis, what we do is we actually collect the amount of carbon dioxide just produced, and we collect the amount of water, basically, that is produced in this reaction. Now, what each of those things are actually a source of is the particular elements that we see. Carbon dioxide is actually the source of carbon. So all the carbon that was ended up in carbon dioxide in this experiment had to come from our organic compounds. Carbon is pretty much where it all came from. The water, all the hydrogen that ended up in the water that we collected came from originally our organic guy. And we could do a calculation similar to what we did earlier, where we were interested in just the one element, not the whole thing. And we could figure out how many grams of carbon we actually started with, since that all ended up in the CO2. We could also figure out how many grams of hydrogen we started with, as that also ended in this H2O. We cannot, though, use the amount of oxygen in each of those that we collected, because oxygen is truly in our organic guy, but we also added some oxygen there that's going to end up in each of those things. So we cannot use the CO2 or the H2O here to figure out the oxygen. But what we do know is that if we do have a compound that is made up of carbon, hydrogen, and oxygen, and we know the mass of the carbon and the hydrogen, we basically can subtract from the sample mass, and whatever is left over will be the grams of oxygen. So we could kind of use that to figure out the grams of oxygen that we would have. So let's take a look at one here and go through the calculation as to how we would do this. So this is sort of the setup here. We throw some oxygen in, we heat it up, the ethanol, it starts to release some water and CO2. We have some absorbers there that will catch all those things. And in this particular case, we started with 11.5 grams of ethanol. Ethanol basically contains carbon, hydrogen, and oxygen, as we've seen previously. And we did collect 22 grams of CO2 and 13.5 grams of water. So we are going to need to use the relationship of CO2, which is 1 mole CO2 will give me 1 mole of carbon, just like we've done before. We will also need to use the relationship from the formula of water, and 1 mole of water will give me 2 moles of hydrogen. So once again, we could use these to get to the moles of hydrogen and the moles of carbon, and then use the molar mass to get the grams of each of those things. We again need to convert CO2 and water into moles, as we have it in grams at this point. So water, which is H2O, to oxygen, 2 hydrogens at 1.008 plus 16 for the oxygen there, going to get us our 18.02 grams per mole as our molar mass of water. Our CO2, 12.01 for the carbon, plus 2 times 16 for the oxygen, will get us there 4401 grams per mole as the molar mass of our CO2. So we're going to start our calculation. We'll start with the CO2. I'm going to do 22.0 grams of CO2. I'm going to use the molar mass here of CO2 on the bottom, the grams, so that they cancel. Gives me moles of CO2. Again, I am not interested in the CO2. I am interested in just the carbon part of that. So now that I have it in moles, I could use my relationship here to go from moles of the whole thing to my moles of carbon, which is 1. And at this point, I am going to get an answer, and I'll tell you why I did get the answer here right now, but it'll make sense later. We'll take our 22 and divide it by 4401. Will give us 0. We'll go 49989 moles of carbon. I now can use that and the molar mass of just carbon to figure out how many grams of carbon that was. And that's 12.01 from the periodic table. The moles of carbon will cancel, and we will end up with about 6.004 grams of carbon. So basically, from this calculation, even though we absorbed 22 grams of CO2, 6 grams of that basically is carbon. And the only source of where carbon could have came from was our sample at the beginning. Now we're going to do the same type of calculation for our water. So we have 13.5 grams of water. We're going to use the molar mass of water, which is 18.02 grams per mole. And if I stop the calculation right at this point, I now have moles of water, and that's what I want because now I can use the formula to go from moles of water to just the hydrogen. Very similar to what I did there with the CO2. 1 mole of water will give us basically 2 moles of hydrogen. And again, I'm going to get an answer here just to make my life easier at the back end of the calculation here. We're going to times it by 2 and divide it by 18.02. Going to give us 1.4983 moles of hydrogen. Now I could go to the periodic table and figure out how many grams of hydrogen that would represent. 1.008 grams of hydrogen per mole. And that's going to be times 1.008 will give us 1.5103 grams of hydrogen. Any questions on those calculations there? So very similar to what we were doing earlier when we did like the nitrogen and caffeine and so forth. Again, that 1.5 grams of hydrogen all had to come from our original sample that we went through our combustion here, our ethanol. As I mentioned before, we unfortunately cannot use the CO2 or the water to figure out the oxygen. But now that we know how much carbon there was and we know how much hydrogen there was, remember that our original sample had a mass of 11.5 grams. And that is the mass basically of the carbon, hydrogen, and oxygen, right? So at this point, what we can do is we can subtract the mass of the carbon that we figured out, that we collected, just basically our carbon. We could also subtract the mass of the hydrogen there, 1.5108. And that will now give me the mass of just the oxygen. That's the only thing that would be left. So 11.5 minus 6.004 minus 1.5103. That will give us 3.9857 grams of oxygen. So again, we're going to use the mass of the sample that is made up of carbon, hydrogen, and oxygen. Since we already now know the grams of carbon and hydrogen, we can subtract it to figure out our grams of oxygen in this case. Any questions on that there? At this point, we can now basically do an empirical form of a problem, right? So we're going to take our grams and convert them to moles. So the reason why I did get an answer for moles here and here is now I don't have to do that calculation. I already did it, right? So that is how many moles that represents 6 grams. That is how many moles represents 1.5 grams of hydrogen. So really at this point, the only thing I need to convert back into moles is my oxygen. So we'll do the molar mass of oxygen, which is 16 grams per mole from the periodic table. Grams will cancel, and we will end up with here 0.2491 moles of oxygen. So now I have my moles of oxygen, I have my moles of hydrogen, and my moles of carbon. So at this point, what we want to do, right, is divide by the smallest number of moles. So what I will do, I think, is we'll go to the next page here. So 0.249. moles of oxygen, 1.4983 moles of hydrogen, and lastly, 0.49989. 0.49989 moles of carbon. All right, at this point, we can see that oxygen actually is the smallest here. So we're going to divide everybody by oxygen. And that is going to give me a 1 for the oxygen. For my hydrogen, that's going to basically give me 6.01. Again, close enough to round in that case at 6.01. We have for my carbon 2.006, which is essentially 2. So we did essentially hit whole numbers, and that will be my empirical formula C2H6O in this case. So combustion analysis basically requires a little bit more calculation up front that you can figure out the amount of hydrogen grams, carbon grams, and oxygen grams. At that point, then you want to convert it into moles, divide by the smallest, and obviously continue on with a normal empirical formula calculation. Any questions on that there? No. So now that we talked about empirical formula here, roll this through. Let's talk about how we determine the molecular formula. So to calculate the molecular formula, you pretty much need 3 things. You need the empirical formula. So if it's given to you, that's great. So you don't have to calculate it. If it is not given to you, then you need to calculate it, obviously. You need the approximate molar mass of your compound. The good news is that one is always given to you in the problem. So somewhere in the problem, they will say this compound has an apparent molar mass of this number. They may even give you a range of numbers, like it may be between like 90 and 100 grams per mole, something like that. If they do give you a range of numbers, you could use anywhere in that range. You could use the low number, the high number, the middle number, whatever one you want to use. And lastly, you need the empirical formula's molar mass. So what you do with those numbers is you take the approximate molar mass that they give you in the problem, you divide it by the empirical formula's molar mass, and that will give you a number. And that number is what you multiply the empirical formula by to get the molecular formula. So let's just say, for example, we had our guy we just did there, something like that. And we did this and we got a 2. What we would then do is multiply everybody in there by 2, and that would give us a molecular formula C6H12O2 would be my molecular formula if this was my empirical formula. Now, when you do this part and you get this number, I will say this is the one place in textbook problems and sort of these calculations that you could be a little bit more generous in the rounding aspect. Because the molar mass a lot of times is like experimentally found, it's approximate, it may be somewhere in that range. You may not get a really pretty whole number all the time when you do this calculation here. So it is probably okay to be a little bit more liberal in terms of the rounding to the nearest whole number. And because the molecular formula and the empirical formula, as we talked about, should be basically related to each other by a whole number ratio, basically. So you can be a little bit more generous in the rounding aspect of it. Question on that there. All right, so why don't you try this one here? A sample compound contains boron, hydrogen. The molar mass of the compound is approximately 30 grams. What is the molecular formula? So boron here is something. Boron here is 10.81. And hydrogen is 1.008. All right. So we're looking for the molecular formula here. Okay, so let's take a look, see how you're doing. So once again, here we're looking for the molecular formula, and we do need three things. We need the empirical formula, which was not given to us, so we do need to calculate that. We need the molar mass of the compound, which was given to us as approximately 30 grams there. And obviously, we need the molar mass there of our empirical formula. So we have to calculate it first before we could do that. So we're going to take our grams and convert them into moles. So we use our molar mass here, 10.81 grams per mole of boron, barium. And we have 1.803 grams of hydrogen, using our molar mass there of hydrogen, 1.008 grams per mole of hydrogen. We're going to take that there, 6.444 divided by 10.81, 0.5961 moles of boron. Do the same thing for our hydrogen here, and we will get 1.7887 moles of hydrogen. In this case, we're going to divide by the smallest, which looks like boron. So we're going to divide them both by our 0.561 here. Going to give us a 1 there, and I believe a 3 right about there. Pretty whole number-ish, I think. And that means that we did hit whole numbers. So we do have our empirical formula of BH3 would be our empirical formula. Now that we have the empirical formula, we do need the molar mass of it. So to get the molar mass of it, we're just going to add up the parts. 10.81 grams per mole for the boron, 3 times 1.008 grams per mole for the hydrogen. And that's going to get us here 13.834 grams per mole. We're going to now figure out our factor that we need to multiply this empirical formula by to get to our molecular formula. So we're going to take the 30 grams, which is our approximate molar mass, divided by 13.834 grams. Not going to times it by 100. So 30 divided by our answer there. It's going to get us basically something like 2.17. As I mentioned before, you could be a little bit more liberal here in the rounding, and you could round that to 2, as again, the molar mass that was given to us was an approximate molar mass, so not the exact number. So we would multiply this by 2, and that would give us B2H6 as our molecular formula. I will say sometimes books and people will write it like this. I'm not a real big fan of it, and just put like the factor on the bottom. I personally would probably prefer just multiplying the number out. But you'll occasionally sometimes see people kind of write it like that, books and stuff like that, but not a big fan. Any questions on that calculation there? Yeah. All right, one last one before we wrap it up here. We want the empirical and molecular formula for this one here. Okay, so let's take a look at this one. Again, in this case, we are given the percent composition by mass of each of these elements. Quick look at the percentages does get about 100% there, so we're not missing anything along the way. We also can get our empirical formula, which is what we need. So we're going to assume 100 grams. Again, what that's going to do is just essentially keep the numbers the same. So we will have 43.64 grams of phosphorus. That would also turn that into 56.36 grams of oxygen. We're going to use our molar mass from the periodic table to convert those into moles so we can get to our empirical formula here. Grams per mole of phosphorus. And 16 there. Grams per mole of oxygen. All right, so we got 43.64 divided by 30.97. 1.4091 moles of phosphorus, 56.36 divided by 16, 3.5225 moles of oxygen. In this particular case, we are going to actually be dividing by phosphorus, it looks like. That's the smallest, 1.4091, 1.4091. That's going to give us a 1. And in this case here, that is not going to give us a 1, but it's going to give us basically a 2.5. That means that based off of this calculation, we have an empirical formula PO 2.5. That, as we talked about before, is a little problematic, right? So we cannot have 2.5. So this, again, is too far to round for the empirical formula. So as we talked about earlier, if we multiply that by 2, that will give us a whole number. So we do want to actually multiply by the factor of 2. So we're going to take this guy basically and multiply both things by 2. That will give us P2O5 as our correct empirical formula. Any questions on that there? That is obviously one thing that we need for our molecular formula. The other thing we need is the molar mass of the compound, which was given to us. So that's the second thing needed. Last thing needed is the molar mass of our empirical formula now that we have it. So to get the molar mass of this guy, 2 times 3097 plus 5 times 16. And that's going to get us something here, 2 times 30.97 plus 5 times 16. Gets us 141.94 grams per mole. We are then going to use our molar mass of our compound that was given to us. Stop there. Which is that. And we're going to divide those two. So we'll take our 283.89 grams divided by our molar mass of our empirical formula. And that's going to give us our factor 283.89 divided by 141.94. Going to give us a factor of 2. That is what we're going to multiply this by, which will give us P4010 as our molecular formula. Question on that there. So I did want to show you one thing here before we officially stop on this, which is in a problem like this where you are given the percent composition by mass of the elements and you're looking for the molecular formula, you could actually kind of start with the molecular formula and actually calculate the empirical formula at the end. So what we know is these percentages here are basically the percentages of the total mass, the molar mass of this compound. So for example, I could take phosphorus and take my percentage and convert it into a decimal, 0.4364, and times it by my 283.89 grams per mole, basically. That is the molar mass of the entire compound. And that will give me 0.4364 times 283.89. It will give me 123.8895 grams of phosphorus, which then I could use my molar mass of phosphorus, which is 30.97 grams per mole, and divide it by 30.97, and I end up with a 4 moles. I could also do the same thing for my oxygen here, which was 56.36, converted into a decimal, times it by the molar mass of the entire compound. And when I do that for my oxygen here, I get 160 grams of oxygen, which I can use the molar mass of oxygen, 16 grams per mole of oxygen. That will give me 10 moles. And what I just calculated there is my molecular formula, which would be P4O10. Once I have my molecular formula, all I have to do is just reduce it down, right? In this case, the only way I can reduce it down is by 2. And if I take this guy and reduce it down by 2, P2O5 would give me my empirical formula. So if you are given the percent composition by mass, you can actually start by calculating the molecular formula first, and then all you have to do is just reduce them down by the simplest whole number, and you'll have your empirical formula. Or as you can see, you could start with the empirical formula and then calculate the molecular formula. If you're not given the percent composition by mass, it's a waste of time to just calculate the percent composition by mass and go that way. You might as well just go the empirical formula way, since you have to do a calculation anyway. So, but if you are given that percent composition, then you'd be good to go. Questions on that?